Our closest galactic neighbor hides 50 of the universe's most bizarre secrets. This is the Small Magellanic Cloud, a dwarf galaxy orbiting our own Milky Way. By the end of this journey, you will know its strangest objects, from stars that behave like cosmic vampires to celestial structures that defy all known physics. We will uncover a runaway star moving too fast for its own age and a supernova remnant that lost its heart. How many cosmic rules can one small galaxy break? The first of our 50 strange objects is a ghost from a cataclysm long past. Designated 1E0102.27219, this supernova remnant is better known to astronomers as E0102. It is a cosmic crime scene where the rules of stellar forensics seem to have been broken. When a massive star dies in a supernova explosion, it typically leaves behind a dense, spinning core called a neutron star. But when researchers pointed their most powerful telescopes at the heart of this expanding cloud of debris, they found nothing. The neutron star is missing. It has simply vanished without a trace. This presents a profound puzzle. Did the star collapse directly into a black hole, leaving no visible remnant? Or did the explosion somehow kick the neutron star out of its own wreckage, sending it flying into the darkness? The mystery of the absent heart is only the beginning of E0102's peculiar story. Its composition is another glaring anomaly. Most supernova remnants are rich in elements like iron and silicon, the heavy ashes forged in the star's final moments. Yet this cosmic bubble is overwhelmingly rich in oxygen, an element usually consumed in the star's interior long before the final blast. It is as if a building made of steel and concrete exploded, leaving behind a cloud of pure, pristine glass. This oxygen-rich nature suggests the star that died was a rare and peculiar type, one that shed its outer layers in a violent tantrum before its core finally gave way. The Chandra X-ray Observatory has given us an unparalleled view of this beautiful wreck. The images reveal a complex, bubble-like structure of glowing gas expanding outward into the surrounding space. Each delicate filament and shockwave is a fossilized imprint of the star's explosive death, a permanent record of the violence that ripped it apart. This intricate structure also tells a story of its environment. The turbulent, low-density nature of the Small Magellanic Cloud has shaped the remnant's expansion, creating a celestial sculpture that would look entirely different in our own crowded galactic neighborhood. E0102 is not merely a cloud of gas, it is a cosmic echo, a portrait of a star's final scream, and a lingering question mark in the faint light of our neighboring galaxy. Far from that silent supernova remnant, another object in the Small Magellanic Cloud screams its presence across the cosmos. This is SMC X-1, a stellar pairing so violent and luminous it has earned the dramatic nickname Beauty and the Beast. The Beauty is a blue supergiant star, a searingly hot sphere of incandescent gas so massive it dwarfs our own sun. It burns with a ferocious, short-lived brilliance, a cosmic titan destined for a spectacular end. But its true nature is defined by its monstrous companion. The Beast is a neutron star, the unimaginably dense corpse of a long-dead sun, and it is feeding. This neutron star does not dine peacefully. Its immense gravity claws vast streams of gas directly from the atmosphere of its giant partner. This stolen stellar material does not fall directly onto the neutron star, however. Instead, it forms a furious, whirling disk of superheated plasma known as an accretion disk, a maelstrom of matter spiraling inward toward its doom. The energy released as this material accelerates and collides is staggering, making SMC X-1 one of the most powerful sources of X-rays in the entire Small Magellanic Cloud. But the system's true strangeness lies in the behavior of this disk. It is not a flat, stable platter of gas. Observations reveal it is warped, twisted like a vinyl record left in the sun. This warp causes the entire disk to wobble or precess, much like a spinning top slowing down. This slow cosmic wobble has a profound effect. From our distant vantage point, the warped disk periodically blocks our view of the furious X-ray source at its center, causing the system's intense light to regularly dim and brighten in a predictable 35-day cycle. This makes the system a perfect natural laboratory. Astronomers can study these eclipses to understand the brutal forces at play, where gravity is so strong it twists space itself and radiation blasts are powerful enough to tear atoms apart. SMC X-1 is a relentless ticking clockwork of cosmic violence, a dance of creation and destruction happening in real time. While the violent ballet of SMC X-1 plays out, a far larger and more enigmatic structure looms in the same galactic neighborhood. N19 is not a single star or remnant, but a colossal cavity known as a superbubble, a void in the cosmos so vast it could swallow entire solar systems. Picture a sphere of empty space hundreds of light years across, its walls sculpted from glowing, turbulent gas. These structures are the cosmic equivalent of a city block being cleared, not by one demolition but by many. Typically, superbubbles are carved by the combined force of stellar winds from massive stars and the shock waves from their eventual supernova deaths, a communal effort that pushes the surrounding gas outward. But N19 defies this straightforward explanation. Its shape is oddly distorted, and the energy required to inflate it seems impossibly high. The standard model of successive star deaths does not quite add up, leaving astronomers with a compelling mystery. One tantalizing possibility is that a recent powerful supernova simply went unseen by our telescopes. A star could have collapsed directly into a black hole with a faint optical display, its explosive energy channeled almost entirely into expanding the bubble's walls. Alternatively, the force might not come from one event, but from a hidden orchestra of stellar power. The bubble could be the work of multiple, densely packed star clusters, each one filled with brilliant, short-lived giants. Their collective stellar winds, like a constant hurricane of charged particles, could be relentlessly pushing on the gas, while their synchronized supernovas deliver periodic, powerful shoves. This would make N19 less a singular structure and more a celestial construction site, a project undertaken by generations of massive stars working in concert. The superbubble is a fossil record of the galaxy's most energetic processes, a silent, expanding testament to forces we are only beginning to comprehend. This runaway pulsar is a stellar corpse with an unstoppable need for speed. Designated B0453-685, this neutron star is hurtling through the sparse gas of the Small Magellanic Cloud like a cosmic cannonball. It moves so fast that it could traverse the distance from Earth to the Moon in a single day. But such immense velocity begs a simple question. What cosmic event could possibly give an object more massive than our Sun such a powerful kick? The most likely explanation is a violent and asymmetrical birth. This pulsar was almost certainly once one half of a binary star system, two stars locked in a mutual orbit. When its more massive partner star reached the end of its life, it did not explode gently. The supernova detonation was so profoundly lopsided that it acted like a natural rocket engine, ejecting the newly formed neutron star from the scene of the catastrophe. The force of that ancient blast sent it careening across the galaxy, a lone fugitive from its own creation. Tracing its path backward is a monumental challenge for astronomers. The galaxy is a crowded and dynamic place, and over thousands of years, gravitational tugs from other stars and gas clouds have subtly altered its trajectory. Pinpointing the exact stellar nursery it fled from is like trying to find the specific pebble that started an avalanche. Yet, even without knowing its origin point, we can witness the dramatic effects of its journey. As this pulsar tears through the thin interstellar medium, it does not travel silently. Its powerful magnetic field and relentless particle wind slam into the surrounding hydrogen gas, compressing and heating it. This creates a magnificent, invisible structure known as a bow shock, a cosmic wave that precedes the pulsar, just like the bow wave that pushes ahead of a speedboat. We cannot see this shock with our eyes, but telescopes sensitive to specific wavelengths of light reveal its faint, shimmering arc. It is a permanent sonic boom written in light, a testament to the raw, untamed power of a star that refuses to stand still. But the chaos of runaway stars and expanding superbubbles is not the only source of strangeness in this small galaxy. Nestled within its faint glow is a stellar nursery of breathtaking beauty and profound mystery, the star cluster known as NGC 346. This is a place of cosmic creation on a grand scale, a vast, swirling cloud of gas and dust illuminated from within by the fierce light of newborn suns. It is one of the most brilliant and active star-forming regions in the entire local group of galaxies, a celestial jewel box sparkling with infant stars. Yet for all its splendor, this cluster holds a deep anomaly that challenges our fundamental understanding of how stars are born together. Standard models of cluster formation suggest that all the stars in a single nursery should be roughly the same age, born from the same collapsing cloud in one concentrated burst of activity. NGC 346 defies this simple story. Here, astronomers find a perplexing mix of stellar generations, brilliant, blue, and incredibly massive young stars, burning fast and furious, shine side by side with a population of older, more established stars. It is as if you walked into a single school classroom and found toddlers playing in one corner while teenagers studied in another. This strange coexistence points to a far more complex history than a single collapse. The evidence suggests that star birth here did not happen in one clean event, but in a prolonged, self-sustaining burst. So what was the trigger for this extended period of creation? The leading theory involves a powerful chain reaction. The first generation of massive stars to ignite would have done so with tremendous force. Their intense radiation and powerful stellar winds began to compress the surrounding gas clouds, squeezing them until they reached a critical density and collapsed to form the next wave of stars. Those new stars then did the same, triggering yet another round of stellar births in a propagating wave of creation. This process turns the entire cluster into a cosmic engine, where the energy output of the first stars directly fuels the birth of the next. The implications of this are profound. If this triggered star formation is common, it means that star clusters are not simple, one-and-done events. They are dynamic, living systems that can engineer their own growth over millions of years. NGC 346 is not just a collection of stars, it is a chronicle of its own violent and beautiful past, a place where the act of stellar birth itself sows the seeds for future generations. The serene glow of a stellar nursery can be deceiving, for within it often lurks a ticking time bomb. R40 is one such object, a luminous blue variable star that represents one of the most unstable and violent stages in a star's life. These are not quiet, steady giants. They are stellar catastrophes waiting to happen, prone to dramatic, unpredictable fits of temper. R40 is a cosmic heavyweight, carrying dozens of times the mass of our own Sun, and this immense bulk is its own undoing. The titanic forces of gravity and radiation within its core are locked in a constant, desperate struggle. This internal battle makes the star profoundly unstable, causing it to swell and contract erratically over periods of months or years. From our distant vantage point, this instability manifests as wild, unpredictable swings in brightness. The star can flare up, becoming significantly brighter, only to fade again for reasons that still puzzle astronomers. It is a star that refuses to follow a predictable script, but the strangeness of R40 is not confined to its flickering light. The star has a terrifying tendency to violently expel its own outer layers into space. These are not gentle stellar winds, but colossal eruptions where the star literally blows off its own skin. Over thousands of years, these repeated outbursts have built up a complex, expanding nebula of gas and dust that now cocoons the central star. This glowing shroud is a direct preview of the star's ultimate fate. The very material we see being ejected today is the fuel that will one day ignite in one of the universe's most spectacular events, a supernova explosion. By studying this nebula, astronomers are essentially reading the diary of a star's final, turbulent chapters before the grand finale. R40 is a rare and precious opportunity to witness a supernova in slow motion, a celestial giant tearing itself apart long before the final, fatal blast. Even the death of a star can be a thing of chaotic beauty. In the faint glow of the Small Magellanic Cloud, a celestial object known as SMC X-1 captures this final act with a strange and twisted elegance. This is a planetary nebula, the glowing shroud of gas cast off by a dying sun, but it defies the classic image of a serene, symmetrical bubble. Instead, its form is violently bipolar, stretched into two opposing lobes that resemble a cosmic hourglass or a butterfly with tattered wings. This chaotic structure is the first clue that this was no ordinary stellar death. The serene, spherical expansion of a typical planetary nebula requires a quiet, solitary star gently releasing its outer layers. The tortured shape of SMC X-1 suggests a far more dramatic and interactive end. The prevailing theory points to a hidden accomplice in this stellar demise. Astronomers suspect the central star is not alone, but is locked in a tight, gravitational dance with a companion star. As the primary star swelled into its red giant phase, its outer layers would have spilled over onto this smaller partner. This transfer of mass would have whirled the gas into a dense, orbiting disk around the companion, a structure known as an accretion disk. This disk then acts like a cosmic nozzle, channeling the gas erupting from the dying star into two powerful, opposing jets. These jets punch their way through the expanding cloud, sculpting the classic bipolar form we see today. It is a stellar death choreographed by a gravitational duet. Yet the nebula's strangeness does not end with its shape. Its chemical fingerprint is equally anomalous. Planetary nebulae are typically rich in elements like nitrogen, which are cooked up in the star's interior and revealed only at its death. SMC X-1, however, shows a surprising deficit of these heavier elements. Its composition is far more primitive, echoing the pristine chemical conditions of the Small Magellanic Cloud itself. This galaxy is known to be less chemically enriched than our Milky Way, having undergone far fewer cycles of star birth and death to seed its interstellar medium with heavy elements. The star that created SMC X-1 lived and died in this more primitive environment. Therefore, the material it ejected is a time capsule, preserving the simpler chemistry of the cloud from which it originally formed. Studying this one peculiar nebula gives us more than just the story of a single star's death. It offers a direct measurement of the galaxy's own chemical evolution, a way to understand how the raw ingredients for planets and life are built up over cosmic time. This beautiful, lopsided ghost is a testament to a galaxy still in its youth, a place where even stellar deaths tell a simpler, more fundamental story. Against the brilliant backdrop of a glowing nebula, a small patch of perfect darkness stubbornly holds its shape. This is the dark globule known as N88A, a dense, cold knot of gas and dust so thick it blocks all light from behind, appearing as a stark, black silhouette against a canvas of incandescent gas. Astronomers classify such objects as Bok globules, and they are often described as the cosmic wombs where future stars are conceived. Within these cold, dark cocoons, gravity slowly works to pull the material inward, potentially collapsing it until nuclear fusion ignites and a new star is born. Yet N88 is far from a typical stellar nursery. Its existence in its current location is a puzzle. this dark globule is not nestled safely in a quiet, cold corner of the galaxy. It is embedded within a bright emission nebula, a region flooded with intense, energetic radiation from nearby massive hot stars. This radiation is a destructive force, a stellar hurricane that should be tearing such a small, fragile cloud apart, preventing it from ever collapsing to form a star. The fact that N88 has not only survived but has maintained its high density tells us something crucial about its internal structure. It must be incredibly massive and tightly bound by its own gravity, acting as a single, resilient unit against the external onslaught. Its survival is a testament to the delicate balance of forces in star formation. It demonstrates that for a new star to be born in a violent neighborhood, the seed must be tough enough to withstand the very environment that might have helped create it. This lone, dark speck is a lesson in cosmic resilience, a quiet, patient argument against the chaos that surrounds it. The silent resilience of a dark globule stands in stark contrast to another resident of this small galaxy, one that refuses to stay put. Racing through the halo of the Small Magellanic Cloud is a stellar fugitive known as HE0437-5439. This is a hypervelocity star, a runaway moving with such incredible speed that it should be escaping the galaxy's gravitational grip entirely. Its velocity is so immense it defies easy explanation, sparking a heated debate about its true origin. The most straightforward theory suggests it was violently ejected from the dense core of a massive star cluster. In such crowded stellar environments, complex gravitational interactions between stars can act like a cosmic slingshot, flinging one member out into the void at tremendous speeds. This would be a purely gravitational origin story, a game of stellar pinball with a single, spectacular winner. Yet there is a compelling and more dramatic alternative. This star might not be a native of the Small Magellanic Cloud at all. Its trajectory suggests it could be an intruder from the Large Magellanic Cloud, our galaxy's other, larger satellite. The two clouds are gravitationally bound to each other and to the Milky Way, and it is conceivable that a star could be ejected from one and captured by the other. This is where the mystery deepens into a full-blown paradox. The star's spectrum reveals it to be surprisingly young, a brilliant, hot blue star only 25 million years old. If it truly began its life in the Large Magellanic Cloud, the journey to its current position would have taken much longer than its apparent age allows. It is like finding a toddler who has just run a marathon that should have taken an adult a lifetime to complete. How can a star be younger than its own journey? Astronomers are forced to consider extraordinary possibilities to resolve this age and travel-time conflict. Perhaps the star was not a single star when it was ejected, but was once part of a tight binary system. In this scenario, the two stars danced dangerously close to the supermassive black hole thought to lurk in the heart of the Large Magellanic Cloud. The black hole's immense gravity could have captured one star and violently flung the other away like a stone from a sling, providing the incredible kick needed for its hypervelocity escape. The single, young star we see today would then be the product of a subsequent merger, two stars colliding and combining during their chaotic ejection to form a single, rejuvenated, and apparently youthful star. This would solve the age paradox by creating a new, younger star from the wreckage of an older pair. The story of HE0437-5439 is a cosmic detective story where the clues of speed, trajectory, and age point to a violent past involving either the densest star clusters or the most powerful gravitational monsters in the local universe. While some stars race across the galaxy, others are locked in a slow, consuming embrace. In the faint constellation of the Tucana, telescopes have pinpointed a system known as RxJ 0049.1-7250, an X-ray binary with a deeply peculiar sense of timing. Here, a compact object, either a neutron star or a black hole, orbits a companion star in a dance that takes not days or weeks, but hundreds of days to complete. This extremely long orbital period is the first clue that something is unusual. Most X-ray binaries whirl around each other in a frantic, close orbit, their violent interactions happening on a timescale of hours. This system, by contrast, is taking its time. The companion star is a massive, aging giant, and the distance between the two objects is vast. This great separation changes the fundamental rules of their relationship. Instead of a constant, raging river of stolen gas, the compact object feeds in fits and starts. The stellar wind flowing from the giant star is thin and sporadic at such a distance, and only when a particularly dense clump of gas wanders too close does the compact object's gravity seize it. This results in the system's second major strangeness, its erratic and unpredictable X-ray outbursts. For long periods, the system can be quiet, almost dormant. Then, without warning, it can flare into one of the brightest X-ray sources in the entire Small Magellanic Cloud, only to fade back into obscurity just as quickly. This on-again, off-again feeding behavior makes classifying the central monster incredibly challenging. Is the compact object a neutron star? We might expect to see pulses of radiation, the lighthouse-like beam from its spinning magnetic field, but none have been detected. Could it then be a black hole? Its mass has not been measured with enough precision to confirm it has crossed that critical threshold. It exists in a ghostly state between classifications, a cosmic vampire whose true nature remains hidden. This ambiguous behavior is more than just a puzzle. It is a vital lesson in accretion physics. The entire Small Magellanic Cloud is a low metallicity environment, meaning it contains far fewer heavy elements than our own Milky Way. This lack of heavy elements makes the stellar winds from its stars thinner and faster. Studying a system like RxJ0049.1-7250 shows us how these unique stellar winds behave under extreme gravity, and how the feeding habits of these cosmic predators change when their galactic environment is built from more primitive, lighter ingredients. This strange, slow binary is a natural laboratory, demonstrating that even the most violent processes in the universe are shaped by the chemical history of their home. This quiet, slow binary system reveals how the galaxy's very chemistry shapes its most violent relationships, but some of the Small Magellanic Cloud's greatest mysteries are not bound to any star at all. They are written in fleeting distortions of light. Astronomers have witnessed a bizarre phenomenon known as gravitational microlensing, a cosmic illusion that acts as a natural telescope. It begins when a dim, compact object, like a rogue planet or a faint star, drifts precisely between Earth and a distant background star in the SMC. The foreground object's gravity, according to Einstein's theory, warps the fabric of space around it. This warped space acts like a lens, bending and focusing the light from the more distant star. From our perspective, the background star temporarily appears to brighten, sometimes by a factor of hundreds, before fading back to its normal luminosity as the lensing object moves on. The entire event is transient, a flash in the cosmic night that can last for days or weeks. The true strangeness emerges when astronomers trace the path of these lensing objects. Some of them do not appear to belong to the Small Magellanic Cloud itself, nor are they part of the foreground disk of our own Milky Way. Their motion and location suggest they are isolated inhabitants of the vast galactic halo, the sparse, spherical cloud of ancient stars and dark matter that surrounds both galaxies. This presents a startling possibility. We could be detecting a hidden population of free-floating planets, ejected from their native solar systems during its chaotic early history, or incredibly faint, failed stars known as brown dwarfs, drifting alone in the immense darkness between the stars. These phantom lenses are effectively invisible to our telescopes by any other means. We only know they are there because of the temporary shadows they cast upon the light of more distant suns. This makes microlensing a unique and powerful tool, a way to map the invisible, dark matter that is believed to make up the bulk of the galaxy's mass. By counting these unseen microlensing events, astronomers can take a census of the unseen, weighing the halo and testing theories about what it is truly made of. Each brief flash of a magnified star is a clue, a single data point in a grand effort to illuminate the darkest corners of our galactic neighborhood. While phantom objects drift unseen in the galactic halo, a much older resident of the Small Magellanic Cloud presents a paradox of time itself. The globular cluster known as NGC 121 is a majestic spherical swarm of hundreds of thousands of ancient stars bound together by gravity for billions of years. It is, without question, the oldest known star cluster in its entire galaxy. Yet when astronomers measured its age, they found a result that defies our expectations. NGC 121 is significantly younger than the oldest globular clusters orbiting our own Milky Way. The difference is not trivial. While the grandest clusters in our galaxy are ancient relics over 12 billion years old, NGC 121 appears to be roughly 1 billion years younger. In the cosmic calendar, that gap is profound. It means that when the very first star clusters were solidifying in the infant Milky Way, the Small Magellanic Cloud had not yet even begun to assemble its most enduring stellar families. This age gap is a crucial clue written in starlight. Globular clusters are the galactic equivalent of fossils, preserving a record of the conditions when a galaxy was first built. The fact that the Small Magellanic Cloud lacks clusters as ancient as our own suggests its early history was fundamentally different. Perhaps it formed its first stars more slowly, in a less dense environment that delayed the collapse into these dense, massive clusters. Or its earliest clusters were simply torn apart by the turbulent gravitational forces of a more chaotic youth, leaving NGC 121 as the sole, slightly younger survivor. This single cluster tells us that the Small Magellanic Cloud experienced a later, or perhaps a quieter, epoch of globular cluster formation. It did not have the same explosive early burst of construction that shaped our own galactic halo. This makes NGC 121 more than just a beautiful collection of old stars. It is a chronological anchor point, a piece of evidence that our galaxy and its small companion, though neighbors, have lived on different cosmic timelines from the very beginning. The silence of ancient star clusters is broken by a pair of stellar behemoths whose partnership defines the very edge of cosmic violence. The binary system HD 5980 is a gravitational dance between two of the most massive stars ever catalogued, each one a searingly hot, blue hypergiant whose combined radiation outshines 1 million suns. Their existence is a precarious one, balanced on a knife's edge between brilliance and self-destruction. The defining moment in their observed history came in 1994, when one of these giants staged a performance that fooled astronomers worldwide. The star erupted in a cataclysmic outburst, briefly blazing with the intensity of a supernova. For a few weeks, it became the brightest stellar object in the entire Small Magellanic Cloud, a flash of light so powerful it seemed to signal the star's final explosive death. Yet when the glare faded, both stars were still there. This was no true supernova, but a super-imposter event, a colossal stellar tantrum where the star violently ejected an enormous shell of its own outer layers without completely destroying itself. It was a warning shot, a preview of an inevitable doom. The cause of such a monstrous eruption is thought to lie in the star's extreme masses. The internal pressure and temperature within these giants are so immense that they push against the very limits of stability. Radiation pressure from within can overcome the star's own gravity, causing its outer envelope to balloon outward until it is ejected into space in a convulsive heave. This is the life of a star living on borrowed time, where the engine at its core is simply too powerful for its own structure to contain for long. The drama does not end with these sporadic eruptions. The two stars are so close that their individual lives are inextricably linked. Each star blows a ferocious, supersonic wind of charged particles out into space, a constant hurricane of stellar material. These two hurricanes are on a permanent collision course. Where the winds meet, they slam together at millions of kilometers per hour, creating a shock front of unimaginable heat. This collision zone glows not in visible light, but in the high-energy fury of X-rays, making the entire binary system a brilliant and variable beacon in the X-ray sky. The ultimate fate of this system is written in its present chaos. These stars are burning through their nuclear fuel at a prodigious rate, and their lifetimes will be astronomically short, measured in only a few million years. One will inevitably explode first as a genuine supernova. The resulting shockwave and the sudden loss of mass would violently disrupt the orbit of the surviving star, likely flinging it away as a runaway or triggering its own premature death. There is also a significant chance that the cores left behind will collapse into black holes, creating a binary system of the darkest objects in the universe, a final, silent testament to a partnership that began in blinding light. This lopsided echo of a stellar death presents a cosmic Rorschach test. IKT-2 is a supernova remnant that completely abandons the classic spherical form we expect from these explosions. Its shape is jagged and profoundly asymmetric, a ragged cloud of expanding debris that looks less like a bubble and more like a shattered piece of celestial pottery. This irregularity is the first and most important clue to its violent history. The pristine, round remnant only forms when a star explodes with perfect symmetry, a uniform blast outward in all directions. The tortured form of IKT-2 tells us the opposite occurred. The detonation of its progenitor star must have been a fundamentally lopsided event, a colossal stellar cannon that fired most of its energy and debris in one preferred direction. This could happen if the star was spinning at a tremendous rate at the moment of its death, or if the complex physics of the explosion itself was biased, channeling energy along the star's magnetic poles like a cosmic jet engine. The alternative, or perhaps additional, explanation lies in its surroundings. A supernova shockwave expands into the existing interstellar medium, the thin soup of gas and dust that fills the space between stars. If that medium is not smooth and uniform, but is instead a chaotic landscape of dense clouds and empty voids, the remnant's expansion will be dramatically distorted. The shockwave will race freely through the low-density areas, while slamming to a near halt against the dense, cold walls of interstellar gas clouds. IKT-2's bizarre shape is therefore a fossilized imprint of two things: the intrinsic violence of its birth and the invisible structure of the space it is expanding into. By meticulously mapping its complex morphology, astronomers are not just looking at a cloud. They are reading a detailed history of the explosion itself and conducting a survey of the interstellar territory, all from a single, beautiful, and broken object. Deep within the faint stellar streams of the SMC, a star is slowly turning itself to soot. Known as ERAS 00483-7347, this is a carbon star, a celestial body in its final, smoldering act. It has exhausted the hydrogen and helium fuel in its core and swelled into a cool, distended giant. In its deepening interior, nuclear fusion has begun to forge a new kind of element, carbon. Through a process called dredge-up, these freshly created carbon atoms are carried by convection currents to the star's surface, fundamentally altering its chemistry. In a star like our Sun, any carbon produced would quickly bond with the abundant oxygen to form carbon monoxide. But in this giant's oxygen-poor atmosphere, the carbon is left free to condense into solid particles, forming a dense shroud of carbon-rich dust around the entire star. This is a stellar smoke screen of cosmic proportions. The resulting dust cloud is the source of the star's greatest strangeness, its intense infrared glow. The star's own visible light, which appears dim and red to our eyes, is actually being absorbed by this surrounding cocoon of soot. The dust grains heat up and re-radiate that absorbed energy, but at much longer, invisible wavelengths in the infrared part of the spectrum. To an infrared telescope, however, ERA's 00483-7347 is not a dim red ember. It is a brilliant beacon, shining far more brightly in this hidden light than it ever could in visible light. This transformation makes it a vital laboratory for understanding one of the universe's most fundamental processes. In the metal-poor environment of the Small Magellanic Cloud, where heavy elements are scarce, the formation of such a prolific dust factory is a delicate and precious event. It shows us how the earliest generations of stars, which were also metal-poor, would have seeded the pristine cosmos with the first grains of carbon dust. These microscopic particles were the building blocks for future planets and ultimately for life itself. By studying this one aging giant, we are witnessing the same kind of process that first polluted the clean emptiness of the early universe with the solid ingredients for everything that was to come. This faint, pervasive glow envelops the entire galaxy like a cosmic atmosphere. Zoom out from individual stars and nebulae, and you will find the Small Magellanic Cloud is not merely a collection of distinct objects, but is immersed in a vast sea of diffuse ionized gas. This is the galaxy's hidden halo, a tenuous hot plasma that radiates a soft, specific wavelength of light. The very existence of this gas is a profound puzzle because it is far hotter and more energized than it has any right to be. For gas to become ionized, its atoms must be stripped of their electrons, a process that requires a tremendous amount of energy, typically from the intense ultraviolet radiation of massive hot stars. Yet when astronomers calculate the energy output from all the known stars and star-forming regions in the galaxy, there is a glaring shortfall. The math simply does not add up. There is not enough visible starlight to explain why this enormous reservoir of gas is so brilliantly illuminated. This is the heart of the missing ionization source problem. Where is all this extra energy coming from? One compelling theory suggests that the galaxy is leaking light. Intense radiation from bustling stellar nurseries, the very engines of star birth, might not be fully contained. These photons could be escaping their local neighborhoods and traveling great distances through the sparse galactic medium, ionizing the gas on a truly galactic scale. It would be like a single, powerful streetlight managing to illuminate not just its own corner, but an entire city valley with a faint, pervasive glow. The alternative explanation is even more intriguing. Perhaps our census of the galaxy is fundamentally incomplete. There could be an entire hidden population of faint, hot stars scattered throughout the SMC. These would be stellar ghosts like white dwarfs or the evolved cores of sun-like stars, which emit vast amounts of ultraviolet radiation while remaining incredibly dim in visible light. This unseen choir of stars, singing in a register our eyes cannot see, could be providing the constant, quiet energy needed to keep the galactic halo shining. Unraveling this mystery is about more than just accounting for a faint glow. It forces us to question what we are really seeing when we look at a galaxy. Is it just the sum of its bright parts, or is there a hidden, energetic infrastructure, a skeleton of ionized gas and faint stars that holds the true key to its structure and history? This diffuse halo is a reminder that sometimes the most important components of a system are not the brilliant points of light, but the soft, pervasive glow that connects them all. This cosmic metronome is skipping a beat. HV829 is a Cepheids variable star, a type of celestial landmark that astronomers depend on to map the vast scales of the universe. These stars are the universe's standard candles, pulsating with a clockwork regularity that directly links their true brightness to the rhythm of their beat. By observing how long each pulse takes and measuring how dim the star appears from Earth, scientists can calculate its distance with remarkable precision. It is a fundamental rung on the cosmic distance ladder, a tool we use to measure everything from the width of our own galaxy to the expansion of the universe itself. But HV829 is a broken clock. Its pulsations are erratic, deviating from the perfect, predictable rhythm that the established models demand. This single star's misbehavior threatens to introduce a subtle but significant error into our most fundamental measurements of cosmic space. So what could cause such a reliable star to go off script? One strong possibility involves a hidden dance partner. If HV829 is not a solitary star but one half of a binary system, the gravitational tug of its companion could subtly distort its pulsations. The companion's gravity might squeeze the star slightly, changing its internal temperature and pressure just enough to disrupt the finely tuned balance between the star's outward radiation pressure and its inward pull of gravity, the very mechanism that drives its rhythmic expansion and contraction. Another explanation lies in the star's chemical makeup. The Small Magellanic Cloud is a low metallicity galaxy, meaning its stars are made from primordial gas that lacks the heavy elements common in our Milky Way. This lack of heavy elements changes how opaque the star's outer layers are, which in turn affects how heat moves through its interior and ultimately governs the stability of its pulsations. A star built from these lighter, purer ingredients might simply vibrate to a different, more complex drum than our standard models, which are largely based on richer, metal-heavy stars. Then there is the star's own internal architecture. Cepheids are not simple, homogeneous spheres. They have complex layered structures with shells of hydrogen and helium undergoing different nuclear processes. Slight variations in the thickness of these layers or in the efficiency of internal convection could create a kind of stellar feedback loop, causing the pulsations to waver over time. Understanding HV829 is not just about solving the mystery of one misbehaving star. It is an act of cosmic calibration. If we can pinpoint the exact reason for its irregular pulse, we can adjust our models to account for this kind of anomaly. This ensures that when we use other Cepheids as mile markers to gauge the distance to far-off galaxies, we are not building our map of the cosmos on a shaky foundation. The true distance to a galaxy, and therefore the true value of the universe's expansion rate, could hinge on our ability to listen carefully to the irregular heartbeat of this one strange star. The erratic heartbeat of a variable star pales next to the violent, sporadic tantrums of another cosmic predator. SMC X-2 is a transient high-mass X-ray binary, a system that spends most of its life in a state of quiet slumber before erupting without warning into one of the brightest X-ray sources in the sky. At its heart lies a neutron star, a city-sized diamond with the mass of a sun, locked in orbit with a massive, hot companion. The drama is not in a constant, violent feeding like its cousin SMC X-1, but in the system's unpredictable and explosive outburst. For years, the system can be almost silent, a faint whisper in the X-ray spectrum. Then, something shifts and the neutron star awakens with a voracious appetite, its X-ray luminosity soaring by a factor of 1,000 or more in a matter of days. These are not gentle flares, but full-scale stellar emergencies. The trigger for this dramatic shift is a delicate and unstable balancing act. The neutron star feeds not from a steady stream, but from the stellar wind flowing from its massive partner. This wind is not smooth and uniform. It is a turbulent, clumpy flow of gas. During quiet periods, most of this wind simply misses the neutron star, flowing past it into the void. An outburst occurs when conditions align perfectly or perhaps imperfectly. A particularly dense clump of gas in the stellar wind might wander too close to the neutron star's gravitational well, suddenly providing a much larger meal. Alternatively, the massive star itself could undergo a minor eruption or a shift in its magnetic field, temporarily boosting the density and speed of its entire stellar wind, turning a light drizzle into a downpour. This sudden influx of material does not fall directly onto the neutron star's surface. It gets caught in an accretion disk, a whirling maelstrom of superheated plasma. As the gas spirals inward, it is compressed and heated to temperatures of millions of degrees, releasing a torrent of high-energy X-ray radiation before it finally plunges onto the neutron star's surface. Studying these outbursts is like watching a cosmic laboratory experiment in real time. Each eruption allows astronomers to measure the magnetic field strength of the neutron star, observe how it channels the incoming material onto its magnetic poles, and calculate the incredible energies involved when matter is subjected to such extreme gravity. The transient nature of SMC X-2 reveals a crucial truth about how neutron stars evolve. They are not always active monsters, but can spend long periods in a dormant state, waiting for the right conditions to ignite their power. This on-off switch is a key part of their life cycle in binary systems, a cycle of fasting and feasting dictated by the turbulent atmosphere of their stellar companions. The violence of a single feeding neutron star is a local drama, but on the far side of the galaxy, an entire stellar metropolis is being built by its own chaotic energy. This is N66, a star-forming region so vast and intricately structured it has earned the name the String of Pearls. It is not one single nebula, but a sprawling complex of glowing gas, dark dust lanes, and brilliant young star clusters, all strung together across hundreds of light years like jewels on a cosmic necklace. The true strangeness of this place is not just its beauty, but its self-perpetuating nature. Here, star birth is a chain reaction, a domino effect of creation where the very act of one star being born sets the stage for the next. The oldest generation of massive stars in this region ignited first. Their ferocious ultraviolet radiation and powerful stellar winds acted like a cosmic bulldozer, slamming into the surrounding clouds of cold hydrogen gas. This immense pressure compressed the gas, squeezing pockets of it until gravity could take over, collapsing them to form the next wave of stars. Those new stars then grew up and began their own work, their radiation and winds pushing outwards to trigger the birth of a third generation. You can see this sequential process frozen in time by looking at the different pearls along the string. One pearl might be a dark, dense globule, a cold cocoon where gravity is just beginning to pull the threads of a new solar system together. Right next to it, another pearl blazes with the light of a young star cluster, its brilliant blue suns having just blown away their natal gas cocoons to shine freely. And further along, the oldest pearl shows a cavity already blown clear by the first stellar generation, its massive stars on the verge of exploding as supernova to begin the cycle all over again. This makes N66 a living chronicle of stellar evolution, a place where you can walk through the chapters of a star's life simply by scanning across the cosmic landscape. It is a perfect demonstration of a universal truth that creation and destruction are two sides of the same coin. The same stellar winds that tear a gas cloud apart also provide the pressure that gives birth to new suns, ensuring the galaxy's great cycle of life continues. A planetary nebula usually glows with the serene light of a dying star, but LIN 41 broadcasts its final act on a different frequency. While most of these stellar ghosts shine brightest in visible light, this object is a roaring beacon in the radio spectrum. Its silence to our eyes is a deafening scream to our radio telescopes. This strange shift in brightness reveals a far more violent and energetic death than we typically see. The serene bubble of a typical planetary nebula forms when a star gently puffs away its outer layers. LIN 41, by contrast, seems to have ejected its atmosphere in a series of furious, convulsive bursts. This created a shell of gas that is exceptionally dense and thoroughly ionized, meaning its atoms have been stripped of their electrons. It is this superheated, charged plasma that makes the nebula so loud in radio waves. Free electrons spiraling in the presence of magnetic fields generate intense synchrotron radiation, a type of emission that naturally dominates the radio part of the spectrum. This suggests the central star is not just fading quietly. It may possess a powerful magnetic field, whipping the expelled gas into a frenzied state, or it might be rotating so rapidly that it flung its material outward with tremendous force. Either way, the star's final moments were chaotic. Studying this radio-loud object gives us a front-row seat to the most extreme mass loss phase of a sun-like star. It shows us that not all stellar deaths are graceful transitions. Some are abrupt, explosive tantrums that leave behind a dense, magnetically charged shroud, a permanent radio broadcast of a star's last defiant shout into the void. This galactic damage is written in stars and gas, a scar stretching across the sky. The Small Magellanic Cloud is not an island, but a satellite caught in a relentless gravitational tug of war with its larger neighbor and our own Milky Way. This cosmic struggle has stretched it beyond its limits, pulling a vast stream of gas and stars out into the void. Known as the Magellanic Bridge and the more distant tidal tail, this structure is one of the strangest objects in our entire neighborhood, precisely because it is not a single object at all. It is a river of celestial debris, a fossilized imprint of past galactic collisions and near misses. The tail is a living archive, recording billions of years of gravitational interaction. As the large and small Magellanic Clouds swing around each other and around our galaxy, their mutual gravity acts like a colossal tidal force, similar to how the moon pulls on Earth's oceans. During a close encounter, this force can become so powerful that it overcomes a galaxy's own gravity, ripping out its outermost stars and hurling its reservoir of raw hydrogen gas into intergalactic space. The resulting stream is a testament to violence on an almost unimaginable scale. By mapping the precise motions and compositions of the stars within this tail, astronomers can rewind the cosmic clock. They can trace the path of this stellar river back to its source, determining not only when the most dramatic encounters occurred, but also what the original Magellanic Clouds looked like before they began to tear each other apart. This river of stars is more than just evidence of past destruction. It is a preview of a future harvest. Much of this stripped material will never fall back into its parent galaxy. Instead, it is destined to rain down upon the Milky Way, providing a fresh supply of pristine gas that will one day fuel the birth of new stars in our own galactic halo. The tail is a bridge of both destruction and creation, a slow-motion capture of one galaxy by another. It shows us that galaxies are not static islands, but dynamic, evolving creatures that grow, change, and sometimes cannibalize each other in the vast dark ocean of space. Some stellar relationships are built on a dangerous dependency. SMC N73 is a symbiotic star, a binary system locked in a celestial pact where one star slowly consumes the other. The arrangement is a delicate and volatile one, pairing a bloated, aging red giant with a dense, searingly hot white dwarf. The red giant is in its final act, having exhausted the fuel in its core and swelled to a distended state. In its deepening instability, it steadily leaks its own atmosphere into space, a gentle but persistent stellar wind. This is where the white dwarf enters the story. This Earth-sized remnant of a long-dead star possesses a gravitational pull so intense it captures a significant portion of this flowing gas. The stolen material does not fall quietly. As it rains down onto the white dwarf's surface, it is compressed and heated to extraordinary temperatures, triggering a relentless, low-level thermonuclear reaction. This process bathes the entire system in intense ultraviolet radiation and creates a complex, glowing nebula that is neither the classic shell of a planetary nebula nor the simple glow of a stellar wind. It is a hybrid structure, a tangled web of gas that tells the story of this ongoing transfer of matter. The true strangeness of SMC N73 and all symbiotic stars lies in their wild and unpredictable mood swings. The system is not a steady source of light. It can flare dramatically in brightness, not by a small fraction, but by a factor of 10 or even 100. These outbursts are not yet fully understood. They may be caused by instabilities in the red giant's wind, suddenly delivering a much denser feast to the white dwarf. Alternatively, the nuclear burning on the white dwarf's surface could itself become unstable, switching from a steady smolder to a violent, eruptive frenzy. This unpredictable variability makes classifying the system incredibly difficult. Is it a quiet binary, a temporary nova, a unique nebula? Its spectrum adds to the confusion, displaying a bizarre mix of emission lines. Astronomers can detect the signature of cool molecular gas from the red giant's outer layers right alongside the searing emission lines from the intensely hot gas swirling around the white dwarf. It is like analyzing the light from a frozen tundra and a blast furnace simultaneously, a combination that should not coexist in a single point of light. Studying SMC N73 is like observing a long-term, slow-motion stellar infection. The white dwarf is feeding, and with every bite, it may be sowing the seeds of its own ultimate destruction. If it accumulates too much mass from its companion, it could cross a critical threshold and be completely obliterated in a cataclysmic type Ia supernova, a final, violent end to a relationship defined by quiet consumption. The slow and silent river of the Magellanic tidal tail is shaped by an invisible hand. The same unseen force that sculpts galaxies on the grandest scale also governs the motions of individual stars within the Small Magellanic Cloud. This dwarf galaxy is more than a collection of strange objects. It is a vital scale for weighing the cosmos's most elusive substance, dark matter. When astronomers chart the rotation of the SMC, they find a profound disconnect between what they see and what the laws of gravity demand. The visible stars and gas clouds are simply not moving in a way that can be explained by the gravitational pull of the luminous matter alone. The outer regions of the galaxy are rotating far too quickly. If only the visible mass were present, those distant stars should be flung out into the void, like children spun too fast on a merry-go-round. The fact that they remain bound to the galaxy means something invisible, something that does not emit or absorb light, is providing the extra gravitational glue to hold everything together. This is the dark matter halo, an immense spherical cloud of unknown particles that envelops the entire visible galaxy. By carefully measuring the velocities of stars at different distances from the galactic center, scientists can map the shape and density of this dark matter container. The results, however, are deeply puzzling. The amount of dark matter inferred for the Small Magellanic Cloud often seems less than what standard cosmological models would predict for a galaxy of its size and type. It appears to be somewhat deficient in this mysterious substance compared to similar dwarf galaxies. This discrepancy is a tantalizing clue. It could mean that the SMC has lost a significant portion of its dark matter halo through its violent gravitational interactions with the large Magellanic Cloud and the Milky Way, a process known as tidal stripping. Just as the visible gas and stars were pulled away to form the Magellanic Stream, so too could the invisible dark matter have been stripped, leaving the galaxy oddly light. Alternatively, the conflict might point to a more fundamental truth about dark matter itself. Perhaps it is not the simple, cold, and non-interacting substance that the simplest models assume. Maybe dark matter particles can interact with each other through some unknown force, creating friction or pressure that changes how they clump around small galaxies. Or the gravity we are measuring could be subtly different on these galactic scales, a hint that our understanding of the laws of physics themselves needs revision. Every star whose motion is tracked in this small galaxy is therefore a data point in a grand experiment. The Small Magellanic Cloud is a natural laboratory, testing our most fundamental ideas about what holds the universe together and what the vast, unseen majority of it is truly made of. A brilliant red star suddenly blazed where none had been before. This mysterious transient event, catalogued as a luminous red nova candidate, erupted in the Small Magellanic Cloud and presented astronomers with a celestial spectacle of rare violence. Its light curve told a story unlike any common supernova. Instead of a rapid blue-white flash, this object brightened slowly and dramatically, its glow shifting intensely toward the red end of the optical spectrum before gradually fading over many months. That specific crimson-dominated signature is the telltale fingerprint of a stellar merger, the cataclysmic collision and union of two stars that were once locked in a close binary dance. The energy released was not from a star exploding in isolation, but from the titanic friction and gravitational energy unleashed as two stellar bodies spiraled inward and smashed together. Imagine two colossal spheres of incandescent gas, drawn so close that their mutual gravity tears them both apart, swirling their material into a single, furious, and temporary fireball. This is the violent birth of a luminous red nova. The event provides a stunning preview of a fate that may await countless close binary systems throughout the universe. Many stars are born in pairs, and over billions of years their orbits can decay. This single red flash in a neighboring galaxy is a rare chance to witness the final, intimate moments of that long gravitational courtship. It shows us that some stars do not die alone but end their lives in a fiery embrace, forging a single, new, and often unstable star from the wreckage of two. The chaotic aftermath of stellar mergers and quiet consumption stands in stark contrast to the raw, exposed power of a Wolf-Rayet star. Among the 50 strange objects in the Small Magellanic Cloud, AB8 is a stellar powerhouse in its final, most violent phase of life. This star has effectively torn off its own skin, shedding its outer hydrogen envelope to reveal the searingly hot, helium-burning core beneath. It is a star that has turned itself inside out, and the result is one of the most extreme environments in the local universe. The surface of AB8 is a maelstrom hotter than almost any other type of star. This incredible heat fuels ferocious stellar winds, which do not gently blow but rather scream into space at velocities approaching thousands of kilometers per second. These winds are a constant supersonic hurricane of charged particles, so powerful that they strip away the equivalent of Earth's entire mass from the star every few hundred years. This relentless self-destruction gives the star its unique and ghostly appearance in a telescope. Instead of a simple, continuous spectrum of light, AB8's light is dominated by intense, broad emission lines. These are the bright fingerprints of different elements being excited in its raging wind. You see the stark imprint of helium, carbon, and oxygen, elements normally hidden deep within a star's interior, now blasted into space for all to see. This is the star's true legacy, its role as a primary foundry for the heavy elements that will one day form new planets and perhaps even life. The carbon in your body, the oxygen you breathe, and the iron in your blood were all forged in stellar furnaces like this one, and then scattered into the cosmos by winds just as powerful. AB8 is a crucial source of this chemical enrichment for the entire Small Magellanic Cloud, polluting the pristine galactic gas with the complex ashes of its own rapid nuclear fusion. Its lifetime is cosmically brief, a fleeting flash of brilliance that will end in a spectacular supernova, seeding its neighborhood with the very elements that make the universe interesting. This self-immolating giant is a vital, if short-lived, chapter in the chemical story of its galaxy. The brilliant death throes of a Wolf-Rayet star are a known quantity, a predictable if violent part of the cosmic cycle. But in the faint light of the Small Magellanic Cloud, there exists a patch of sky that emits a form of energy far more powerful, with no source to explain it. This is an unidentified gamma-ray source, a specific location that screams its presence in the highest energy photons the universe can produce, yet offers no visible face. Gamma rays are the most energetic form of light, born from the most extreme processes in nature. They are the signature of matter pushed to its absolute limits, the final scream of particles accelerated to nearly the speed of light. When our most powerful telescopes, like the Fermi Gamma Ray Space Telescope, scan the heavens, they see this one particular spot in the direction of the SMC glowing brightly. But when astronomers turn their optical and X-ray telescopes to the exact same coordinates, they find only darkness and silence. There is no bright star, no churning nebula, no supernova remnant. It is a shout with no visible shouter, a cosmic ghost that haunts the high-energy spectrum. So what could possibly be generating this immense power while remaining completely invisible? One compelling theory points to a hidden choir. The source could be a dense population of pulsars, the spinning neutron stars we have encountered before. Each one is a natural particle accelerator, its immense magnetic field whipping charged particles to incredible speeds, causing them to emit gamma rays. Individually, each pulsar might be too faint and distant to spot, but together as a collective, their combined gamma ray hum could create the bright, unresolved glow we detect. It would be like hearing the roar of a massive crowd from a great distance without being able to pick out any single voice. A far more exotic possibility involves the galaxy's unseen component, dark matter. Some theories suggest that dark matter particles, when they collide with one another, could annihilate each other in a flash of pure energy, producing gamma rays as their final signature. If this is the case, then this mysterious patch of sky could be a place where the dark matter halo of the Small Magellanic Cloud is unusually dense. A place where these invisible particles are colliding with such frequency that they create a beacon we can finally see. We would be witnessing the indirect evidence of the universe's most elusive substance, not through its gravity but through its self-destruction. Or perhaps the truth is something entirely new. It could be a previously unknown type of high-energy accelerator, a natural cosmic machine that operates on principles we have not yet discovered. This represents the absolute cutting edge of a new era in astronomy, known as multi-messenger astronomy. It is the practice of using every type of signal the universe sends us, from gravity waves to neutrinos to different kinds of light, to piece together a complete picture of a single event or object. Here, the only messenger is the gamma ray photon itself, a lone clue from a crime scene we cannot otherwise see. This unidentified source is more than just a mystery, it is a direct challenge. It forces us to admit that for all we have learned about our neighboring galaxy, there are still forces at work here that operate in the shadows, generating unimaginable power while leaving no other trace. The hunt for its true identity is a race between conventional and exotic explanations, a fundamental question about what is left to discover in our own cosmic backyard. A star cluster should be a portrait of stellar uniformity, a single generation born from the same cosmic womb. Yet within the brilliant swarm of NGC 330, the Hubble Space Telescope captured a fundamental crack in that assumption. Its color magnitude diagram, the essential fingerprint of any star cluster, revealed not one but two distinct main sequences. This is the equivalent of a family portrait showing two completely different sets of parents. The main sequence is the stable, adult phase of a star's life, a direct relationship between its color and its intrinsic brightness. In a normal cluster, all the stars fall along a single, clean line. But here, the stars are cleanly divided into two separate, parallel lines. They are not mixed together. They are two distinct populations living side by side in the same gravitational embrace. The most likely explanation for this cosmic duality is a stark difference in chemical composition. One population appears to be made of pristine, primordial gas, poor in heavy elements. The other population is richer in metals, the heavier elements forged in the hearts of earlier stars. This presents a timeline of creation. The first generation of stars formed from the cluster's original, pure hydrogen and helium. Those massive, short-lived stars then lived and died in spectacular supernova, polluting the cluster's remaining gas with their newly forged heavy elements. Then, a second generation of stars coalesced from this newly enriched material. The presence of these extra metals changes the very physics of a star. A metal-rich star is more opaque, which affects how it burns its fuel and, crucially, how it appears in a color magnitude diagram. It will sit in a slightly different position than a metal-poor star of the same mass, creating the observed split. This two-step formation process shatters the classic view of globular clusters as simple, one-and-done events. NGC 330 is not a single snapshot of star birth but a layered chronicle. It proves that a cluster can retain enough of its gaseous raw material after the first stellar generation explodes to build a second, chemically distinct family. This forces us to rethink the life cycle of these dense stellar cities, revealing them as more dynamic and self-renewing than we ever believed, capable of engineering their own chemical evolution from within. The sheer scale of these structures defies easy comprehension. LHA-115N19 is a supershell, a cavity in the interstellar medium so colossal it makes even the largest superbubbles seem modest by comparison. Think of a single bubble blown by a child compared to a weather system spanning an entire continent. This is a structure born from generations of stellar violence, a monument to collective power. The leading theory for its creation is the coordinated death of stars. Over millions of years, dozens of massive stars within the shell's central cluster would have lived their short, brilliant lives and then died in successive supernova explosions. Each blast delivered a powerful shove to the surrounding gas, and together, their combined shockwaves carved out this immense void, pushing the interstellar medium outward to form a single, unified shell hundreds of light years across. But the story does not end with a simple expansion. This concentrated release of energy may have created something even more dramatic, a galactic chimney. In this model, the combined force of so many supernovas did not just push gas sideways, it punched a hole straight up and down through the thinner parts of the galactic disk. Hot, metal-enriched gas from all those explosions could then vent directly out into the galactic halo, a smokestack releasing the processed remains of dead stars into the vast intergalactic medium. This process is a crucial form of galactic feedback, a way for a galaxy to regulate its own star formation by expelling the very gas that would otherwise collapse to form new suns. Yet, a persistent debate simmers among astronomers. Could a single, unimaginably energetic event have forged this supershell instead? The contender is a hypothetical supernova triggered by the collapse of a supermassive star, a behemoth with hundreds of times the mass of our Sun. Such an explosion would release more energy than dozens of ordinary supernovas at once, a single, definitive blast that could potentially inflate a structure like LHA-115N19 in one catastrophic moment. While evidence increasingly favors the collective model, the mere possibility of such a solitary cataclysm keeps the mystery alive, reminding us that the universe always reserves the right to break its own rules with spectacular force. While the universe often shouts its mysteries in bursts of gamma rays, some secrets are whispered in a slow, rhythmic pulse. The red giant star HV11417 is one such cosmic metronome, a mirror variable star whose heartbeat takes nearly 400 days to complete a single cycle. This ancient star is in its final, unstable act, having exhausted the hydrogen fuel in its core and now burning helium in a shell around a dense core of carbon and oxygen. This delicate balancing act makes the entire star breathe, swelling and shrinking over its long year. As it expands, its outer layers cool and dim, only to contract and heat up again, brightening dramatically. The change is not subtle. Its visible light output can vary by a factor of several hundred, transforming it from a faint ember to a brilliant beacon and back again. This predictable rhythm makes mirror variables like HV11417 crucial cosmic yardsticks. Their very pulse is linked to their true, intrinsic brightness, allowing astronomers to use them as standard candles to measure vast distances across intergalactic space. But the true strangeness of this particular star emerges when we observe how its light reaches us. The journey from the Small Magellanic Cloud to Earth is not through a perfect vacuum. It is a trek through a fog of interstellar dust. This dust, composed of tiny silicate and carbon grains, acts like a cosmic filter. It scatters and absorbs the star's blue light more effectively than its red light, causing the star to appear both dimmer and redder than it truly is. This is the same effect that makes the Sun look deep red at sunset as its light passes through more of Earth's atmosphere. For HV11417, this interstellar dust screen provides a unique scientific opportunity. By meticulously measuring how much its light is dimmed and reddened at different points in its pulsation cycle, astronomers can conduct a forensic analysis of the dust itself. And the dust in the Small Magellanic Cloud is fundamentally different from the dust in our own Milky Way. Our galaxy is metal-rich, having been cycled through many generations of stars, which has created dust grains that are large, complex, and efficient at blocking light. The Small Magellanic Cloud, by contrast, is a low metallicity environment. It lacks the heavy elements needed to build large, fluffy dust grains. Its interstellar dust is more primitive, composed of smaller, sharper, and more transparent particles. This difference changes everything about how starlight is processed. The dust in the SMC is less effective at blocking light, but may be more efficient at reddening it in specific ways, creating a unique spectral fingerprint. Each pulsation of HV11417 sends a new pulse of light through this cosmic filter, allowing scientists to map the size, composition, and distribution of these alien dust grains with incredible precision. This one pulsating giant is not just a distant sun, it is a brilliant probe light illuminating the invisible, dusty infrastructure of its own galaxy. Some stellar partnerships are built on a repeating cycle of theft and detonation. In the faint stellar streams of the Small Magellanic Cloud, one particular binary system has earned the ominous title of a recurrent nova, a ticking time bomb that has erupted into brilliance not once, but multiple times throughout recorded history. This is a system where a white dwarf, the Earth-sized cinder of a dead star, orbits perilously close to a more normal, hydrogen-rich companion. The white dwarf's immense gravity acts as a celestial siphon, relentlessly pulling a stream of hydrogen gas from its partner. This stolen material does not simply land on the surface. It accumulates in a dense, degenerate layer, piling up like unspent fuel on a nuclear furnace. For decades, the process is silent and invisible, a slow, steady accretion. Then, a critical threshold is crossed. The base of this hydrogen layer becomes so incredibly hot and dense that it ignites in a runaway thermonuclear fusion reaction. The entire accumulated layer detonates in a flash of unimaginable power, causing the system to flare in brightness by a factor of tens of thousands. From our perspective, a faint, anonymous point of light suddenly becomes a brilliant beacon, outshining entire nebulae for a brief, spectacular period before fading back into obscurity. This is not a supernova which destroys the star. This is a surface explosion, a stellar flare-up that leaves the white dwarf intact, ready to begin the entire cycle of theft and accumulation all over again. This repetitive nature is what makes recurrent nova so crucial to understanding one of cosmology's most important tools, the Type Ia supernova. These supernovae are the brilliant standard candles used to measure the expansion of the universe, but their exact origin has been a subject of intense debate. The leading theory points directly to systems like this recurrent nova. The logic is terrifyingly simple. With each nova cycle, the white dwarf survives and the process of accretion begins again. If the rate at which it steals hydrogen is just right, it may not eject all of the material it gained in the explosion. Over thousands of cycles, the white dwarf could slowly, inexorably gain mass. And for a white dwarf, there is a strict upper limit, a point of no return known as the Chandrasekhar limit. If its mass creeps too close to this boundary, the entire star, not just its surface layer, will become gravitationally unstable. The result is not a surface flash, but a total thermonuclear conflagration that rips the white dwarf apart completely, unleashing the energy of a Type Ia supernova. Therefore, every eruption we observe from this recurrent system is a potential step toward its own ultimate annihilation. It is a laboratory for stellar suicide, a chance to watch the prelude to one of the universe's most decisive explosions unfold in real time, cycle by patient, violent cycle. Within the sprawling, tangled wreckage of the supernova remnant N49, a single piece of shrapnel races ahead of the rest. This cosmic bullet, a dense knot of stellar material, is hurtling through space at a staggering velocity of over 5 million miles per hour. It moves so fast that it has already punched clear through the main shell of the expanding nebula, leaving a visible trail of shocked and glowing gas in its wake. This is not merely a clump of general debris. This specific projectile holds a unique chemical fingerprint. Spectroscopic analysis reveals it is rich in elements like neon and oxygen, a composition that points directly to its origin. This bullet is not just gas from the explosion, it is a piece of the star's own deep interior, a fragment of the progenitor star that was violently shot out during its final catastrophic collapse. For decades, astronomers have theorized that core collapse supernova are fundamentally lopsided events, but this object provides the first direct, tangible evidence. Instead of a perfectly spherical blast, the detonation must have been profoundly asymmetric, channeling immense energy in one direction like a titanic cannon. The bullet is a piece of the star's very heart, a relic from the moment of its death that was ejected with such force it escaped the expanding fireball entirely. This single, fast-moving knot rewrites our understanding of a star's final moments. It shows us that the collapse is not a uniform crushing, but a chaotic, directional rupture where the very core of the star can fragment, with pieces flung across space at unimaginable speeds. By studying this one fragment, we are holding a piece of the stellar engine itself, examining the raw materials and the unimaginable forces that govern the death of a cosmic giant. This faint, sprawling halo is a ghost from the galaxy's violent childhood. Recent observations have fundamentally reshaped our view of the Small Magellanic Cloud, revealing it is far larger than the bright, central bar we see with the naked eye. This dwarf galaxy is wrapped in a vast, diffuse shroud of ancient stars, a stellar halo that stretches far into the emptiness of intergalactic space. It is a structure of profound silence and immense age, a celestial archaeology site where the galaxy's deepest history is written in faint, scattered points of light. To understand how this halo formed, we must look back to the beginning. Galaxies are not born in isolation, they are built through a relentless process of cosmic cannibalism. In its youth, the Small Magellanic Cloud would have been surrounded by a retinue of smaller, weaker dwarf galaxies and star clusters. Over billions of years, the SMC's gravity would have torn these satellites apart, capturing their stars and stitching them into its own outer fabric. This extended halo is the fossilized evidence of that ancient feast, a graveyard of devoured galaxies whose stars now orbit as a silent tribute to their violent assimilation. The structure of this halo is therefore a direct record of the galaxy's assembly. Unlike the ordered rotation of the central disk, the halo stars move in chaotic, randomly oriented orbits like a swarm of bees. This disordered motion is the telltale signature of an accretion history, a dynamic that could not have arisen from a quiet, internal collapse. By mapping the motions and chemical compositions of these halo stars, astronomers can perform a form of galactic genealogy. They can identify groups of stars that share a distinct chemical fingerprint and a common orbital path, tagging them as the remnants of a single, long-lost dwarf galaxy that was consumed. It is like finding distinct tribes with unique languages and customs within a larger nation, each one telling the story of a different homeland. The very existence of this halo solves one mystery while deepening another. It confirms the hierarchical model of galaxy formation, where large structures build themselves from smaller ones. Yet, the specific properties of the SMC's halo are strangely deficient when compared to predictions. Its stellar population is sparser, and its total mass seems lower than expected for a galaxy of its size. This discrepancy points directly back to the galaxy's violent interactions with its neighbors. The same gravitational tides from the large Magellanic Cloud and the Milky Way that pulled out the Magellanic Stream may have also brutally stripped away a significant portion of the SMC's outer halo, scattering its ancient stars into the void. This faint, extended glow is more than just a border. It is a testament to survival in a hostile cosmos, a reminder that even galaxies must fight to hold onto their own history. Deep within a dark nebula of the Small Magellanic Cloud, a star is fighting to be born. This is the young stellar object known as M2002 SMC 055188. A protostar still swaddled in the thick, cold cocoon of its own creation. To our eyes, this region of space is a perfect void, a patch of empty blackness, but peer into it with an infrared or radio telescope, and the darkness ignites into a brilliant, chaotic nursery. The infant star at the center is still gathering mass, pulling in gas and dust from a vast, whirling disk that feeds it like an umbilical cord. All of this is shrouded by an opaque envelope of material, a cosmic womb so dense that not even the fiercest light from the nascent star can yet escape. We are witnessing the very first steps of stellar infancy, a process normally hidden from view. What makes this particular young stellar object so vital to science is its address. The Small Magellanic Cloud is a low metallicity galaxy, meaning its gas and dust contain far fewer heavy elements like iron, silicon, and carbon than the interstellar clouds in our own Milky Way. This primitive chemical makeup is a throwback to the early universe, a time before countless generations of stars had lived and died to pollute the cosmos with these heavier ashes. When we study a star forming here, we are observing the process under pristine conditions. It answers fundamental questions about how the very first stars in the cosmos came to be. Does the lack of heavy elements make it easier or harder for a gas cloud to collapse? How does it affect the size and temperature of the resulting star? The dust grains in this cloud are different, smaller and sharper, which changes how efficiently they can cool the cloud and allow it to fragment. In the metal-rich nurseries of our galaxy, dust acts as a powerful coolant, radiating heat away and enabling the cloud to break into smaller clumps that form smaller stars. Here in the SMC, the cooling is less efficient. This might lead to the formation of more massive stars, on average brilliant behemoths that live fast and die young, or it could change the very dynamics of the accretion disk feeding the newborn sun. M2002 SMC 055188 is a single point of light, but it illuminates the origin of all stars. By decoding the physics within its dusty shroud, we are essentially looking back in time, watching the universal recipe for star formation as it was written in the very beginning. This faint whisper in the radio spectrum reveals a cloud that refuses to follow the rules. While much of the Small Magellanic Cloud rotates in a predictable galactic dance, one specific cloud of neutral hydrogen gas moves to its own secret rhythm. Astronomers detect this cloud not by its light, but by the faint radio waves emitted by its hydrogen atoms, a signature known as the 21-centimeter line. This invisible structure is designated as an anomalous HI cloud, and its strangeness lies in its motion and its stillness. Its velocity is subtly but definitively different from the surrounding galactic material, as if it is drifting through the galaxy like a ghost ship on a wayward current. This velocity anomaly is a fossilized clue to a violent past. One compelling possibility is that this cloud is the debris from a past collision, a shred of a smaller dwarf galaxy that was torn apart by the SMC's gravity billions of years ago. The cloud's unique motion could be the last echo of that ancient merger, a pocket of gas that never fully settled into the galaxy's smooth rotation. Alternatively, the cloud might not be a relic of destruction but a herald of construction. It could be a clump of pristine, intergalactic gas, a fresh influx of raw material falling into the galaxy for the very first time. This would be a slow, quiet form of cosmic rainfall, providing new fuel for future generations of stars. Yet for all this potential, the cloud remains strangely and profoundly silent. It is a reservoir of hydrogen, the primary ingredient for star birth, and yet it shows no signs of collapsing to form new suns. It is a cosmic desert in the middle of a fertile galactic plain. This suppression of star formation is its second major mystery. The cloud may be held in a state of suspended animation by powerful internal magnetic fields, whose lines of force act like a cage, providing enough pressure to resist the inward pull of gravity. Or the gas within the cloud could be too turbulent, with chaotic internal motions creating a kind of energetic buffer that prevents the quiet, localized collapses needed to ignite new stars. This invisible, quiet, and motionally distinct cloud is a stark reminder that the empty spaces between the stars are just as important as the stars themselves. It is a strange player in the galactic ecosystem, a pocket of potential that holds the secrets of the galaxy's past and the keys to its future, all while remaining dark, silent, and utterly still. The serene glow of a stellar nursery can hide a star wrapped in its own private nebula. SMC 0189 is a BE supergiant, a rare and contradictory beast that shines with the fierce blue heat of a young, massive star, yet is swaddled in the cool, dusty shroud of an old one. Its spectrum reveals the star's strange duality. Alongside the expected hydrogen emission, we see the stark, forbidden lines of elements like iron. In the near vacuum of space, certain atomic transitions are normally impossible, forbidden by the laws of quantum physics. For these lines to appear so brightly, the atoms must be embedded in an unusually dense and calm environment, a place where they can be excited without constant collisions disrupting them. This points to a vast, orbiting disk of gas and dust, a tranquil celestial moat encircling the raging stellar giant. The origin of this dense, dusty ring is one of the most heated debates in stellar astronomy. Is this the signature of a dramatic stellar partnership? The star could have a hidden, smaller companion whose gravity violently stripped away its outer layers, spinning the stolen material into a vast, flat disk that now obscures our view of the central drama. This would be a cosmic crime scene where one star is slowly consuming the atmosphere of another. The alternative is a story of profound internal instability. Perhaps SMC 0189 is a single, supremely unstable star undergoing such extreme, episodic mass loss that it puffs its own atmosphere out into space. Slow, dense winds from its equator could coalesce into this dusty torus, while fiercer, faster winds blast out from its poles. This would make the star a cosmic fountain, simultaneously building its own cage and trying to blast its way out of it. Each explanation paints a vastly different picture of the star's past and its ultimate fate. A binary interaction could eventually lead to a spectacular merger or a supernova triggered by mass transfer. A single, unstable star might be on the verge of erupting as a luminous blue variable or collapsing directly into a black hole. SMC 0189 is a celestial riddle, its beautiful, forbidden light hinting at a hidden story of either a destructive dance or a solitary, violent struggle against its own immense power. A brilliant pinprick of X-ray light in the Small Magellanic Cloud defies every known category of cosmic object. This is an ultraluminous X-ray source, a beacon so powerful it outshines any normal stellar black hole or neutron star binary. Yet it is far too small and isolated to be the supermassive black hole at the center of a galaxy. It burns with the ferocity of millions of suns, all focused into a single, relentless stream of high-energy radiation. The sheer power it emits pushes against a theoretical limit known as the Eddington limit, a point where the outward pressure of radiation should be strong enough to halt the inward flow of matter, effectively turning off the accretion process. Yet this object shines far beyond that boundary, as if its cosmic engine has found a way to ignore the fundamental rules of physics. How can it consume matter so greedily without blowing itself apart? The leading theory points to a hidden monster, an intermediate mass black hole. This would be a celestial giant with a mass thousands of times that of our Sun, a missing link between the stellar mass black holes formed from collapsing stars and the supermassive behemoths that lurk in galactic cores. Such an object would have a deeper, stronger gravitational well, allowing it to pull in and process vast amounts of material without the radiation pressure stopping the feast. The infalling gas would not need to be as densely packed to explain the incredible luminosity, neatly sidestepping the Eddington limit. But there is a compelling and stranger alternative. What if the black hole is not a middleweight champion, but a common stellar mass black hole in a state of extreme and gluttonous consumption? In this scenario, the accretion disk feeding the black hole is not a flat, stable platter. It could be puffed up into a thick, dense torus, a donut of superheated gas that traps its own radiation. This trapped light exerts an inward pressure, actually helping to force more material down the black hole's throat in a continuous supercritical flow. It is a cosmic feedback loop of consumption where the energy released by feeding does not stop the meal but instead intensifies it. The specific ultraluminous source in the SMC provides crucial evidence in this debate. Its X-ray spectrum shows peculiar dips and features that suggest we are viewing its accretion disk from a specific, perhaps edge-on angle. This perspective allows astronomers to probe the geometry of the inflowing material, searching for the telltale signs of a thick, obscuring structure that would support the supercritical accretion model. Every flicker in its high-energy output is a clue, a data point in a grand experiment to understand how the darkest objects in the universe can become the brightest. This one strange point of light forces us to rewrite the manual on black hole feeding habits, revealing that under the right conditions, their hunger can become truly limitless. These faint rivers of stars flow not between galaxies, but within the very heart of the Small Magellanic Cloud itself. They are stellar streams, the cosmic equivalent of ancient ruins being slowly reclaimed by the jungle. Unlike the Grand Magellanic Stream torn out by external forces, these are internal scars, the dissolving remnants of smaller star clusters and even dwarf galaxies that the SMC has consumed over billions of years. They are the galaxy's own ghostly fingerprints, evidence of a quiet, persistent cannibalism happening right in our cosmic backyard. Mapping these faint, wispy trails is an act of galactic archaeology. Each stream is a fossilized timeline, a river of stars that still remembers the path of its original orbit before its parent cluster was torn apart. By tracing their delicate arcs across the sky, astronomers can rewind the clock, calculating not just when these mergers happened, but what the original structures looked like before they were devoured. It is a way to reconstruct the galaxy's family tree, identifying long-lost stellar siblings that have now been fully assimilated into the larger population. The very existence of these streams reveals the relentless work of internal gravitational forces. The SMC is not a smooth, static disk, it is a dynamic and churning system. As these smaller clusters orbit within the galaxy, they feel a differential gravitational pull, the same kind of tidal force that the Moon exerts on Earth's oceans. The side of the cluster closer to the galactic center is pulled more strongly than the far side. Over millions of orbits, this relentless stretching overcomes the cluster's own gravity, pulling it apart like cosmic taffy. The stars are not destroyed, they are simply released from their gravitational bonds, left to drift in their original orbital path as a faint, extended stream. This process is a delicate balance between creation and dissolution. Some of these streams are so fresh and coherent that their origin is still obvious, a clear line of stars pointing back to a specific, now disrupted cluster. Others are so old and thoroughly mixed that they are little more than a slight statistical overdensity, a whisper of structure hidden within the general starlight. Studying these different stages is like watching a time lapse of a galaxy digesting its meals. The most pristine streams tell us about the recent past, while the faint, smeared-out ones speak to the deep, chaotic history of the galaxy's formation. This internal cannibalism is a fundamental part of the SMC's growth. Every stream represents a successful capture, a time when the galaxy added more mass and more stars to its inventory. By counting these streams and measuring their masses, we can begin to understand how this small galaxy built itself up from smaller pieces, a bottom-up construction that mirrors the formation of the largest galaxies in the universe. These silent, flowing rivers of suns are a living history book, their pages written not in ink but in the positions and motions of a billion distant points of light. Even as stars fight to be born in shrouded nurseries, some succeed and immediately begin building their own celestial families. Around these infant suns in the Small Magellanic Cloud, astronomers have found the faint, telltale glow of protoplanetary disks, the swirling rings of gas and dust where planets are born. These are not yet confirmed worlds, but the raw construction sites for entire solar systems. Yet the building materials available here are fundamentally alien. The Small Magellanic Cloud is a metal-poor environment, meaning it lacks the heavy elements like iron, silicon, and carbon that are the essential ingredients for rocky planets like Earth and the cores of gas giants like Jupiter. The dust grains in these disks are not the complex, fluffy particles common in our galactic neighborhood. They are smaller, sharper, and more transparent, composed of simpler, more primitive substances. This scarcity of heavy elements changes the entire planet-building recipe from the very first step. In our own solar system, planet formation began when microscopic dust grains, rich in metals and silicates, gently collided and stuck together, eventually snowballing into kilometer-sized planetesimals. But in the SMC, that delicate process of dust coagulation faces a severe shortage. With fewer heavy elements available, the initial seeds for planets are rarer and slower to grow. Could this mean that rocky, terrestrial worlds are a cosmic rarity in such a primitive galaxy? Or does nature simply find a different path? One possibility is that the lack of efficient cooling from metal-rich dust leads to the formation of much larger and more massive gas giant planets. Without as many solid cores to act as anchors, the process might rely more on the direct gravitational collapse of vast swaths of the protoplanetary disk, birthing bloated, hydrogen-rich worlds far larger than Jupiter. These would be planets without a solid heart, vast spheres of gas orbiting their young stars. The architecture of these emerging solar systems could be profoundly strange. The weaker dust grains might not be able to sustain the fierce, grinding forces inside the disk, preventing them from growing into the robust planetary building blocks we know. This could result in a disk that forms fewer but far more massive planets on wildly eccentric orbits, a gravitational free-for-all where the strongest worlds consume all the available material. Alternatively, the entire system might be stillborn, with the disk simply unable to assemble planets at all, its material slowly dissipating back into space or falling into the central star, leaving behind a solitary sun in an empty cosmic neighborhood. The protoplanetary disks of the SMC are a glimpse into a different kind of cosmic evolution. They show us that the path from dust to planets is not a universal given, but a delicate process shaped by the chemical history of an entire galaxy. The worlds that might eventually form here would be alien in the truest sense, built from a different set of elemental bricks under a different set of physical rules, forever changing our understanding of what a planet can be. While most stars churn their interiors into a uniform blend, one strange sun in the Small Magellanic Cloud presents a surface of pure, concentrated anomaly. This chemically peculiar star is a cosmic refinery, its atmosphere bizarrely enriched with specific heavy metals like mercury and europium, elements that should be buried deep within its core. It defies the natural churning action that normally mixes a star's contents, presenting a surface that is fundamentally different from the layers beneath. The secret to this strange segregation is a powerful, organized magnetic field, a rigid cosmic cage that holds the star's atmosphere in a strange and quiet grip. Within this magnetic prison, the normal forces of stellar life are suspended. Radiation pouring from the star's core pushes upward on the atoms in its atmosphere. For most elements, this push is not enough to overcome gravity, and they slowly sink. But for a select few, like mercury and europium, the push is just right. The radiation selectively lifts these specific atoms, floating them to the surface like corks in water, while other, heavier elements are left to sink into the stellar depths. It is a slow, relentless process of cosmic sorting, creating a thin, shimmering skin of rare metals atop the star. Observing this phenomenon in the Small Magellanic Cloud is a unique experiment because here, the galactic environment itself is a variable. This dwarf galaxy is metal-poor, meaning the primordial gas from which this star formed was deficient in all heavy elements. Yet, on its surface, we see a dramatic overabundance of a select few. This forces us to ask, how does the strength and structure of a magnetic field and the resulting chemical sorting change when the star begins its life with a much simpler, purer chemical palette? Does the process become more efficient, creating even more extreme surface anomalies when there is less competition from other metals? Or does the weaker initial metallicity produce a different, perhaps more fragile, magnetic field structure altogether? This one strange star is a laboratory for stellar atmospheres, a place where we can watch the fundamental physics of element separation play out under conditions that are a direct throwback to the early universe. Its peculiar light is a direct message detailing how magnetism can sculpt a star's very face, creating a celestial chemist's dream in the faint glow of our neighboring galaxy. Beyond the brilliant pinpricks of black holes and neutron stars, the entire Small Magellanic Cloud is whispering in a language of high energy. A faint, diffuse glow of X-rays bathes the galaxy, a soft, pervasive light that exists in the spaces between every known object. This is not the focused scream of a single cosmic predator, but the combined murmur of an entire galactic ecosystem. Its origin is one of the most stubborn puzzles in modern astronomy, a question of whether we are hearing a cosmic crowd or the sound of the galaxy breathing. The most straightforward explanation is a hidden choir, a vast population of millions of faint, unresolved stellar sources. Imagine standing in a city at night, too far away to see any individual streetlights or car headlights, but seeing the entire urban glow on the horizon. This galactic glow could be the combined X-ray output of countless white dwarfs accreting material from companion stars, or active binaries where stellar winds collide and heat gas to extreme temperatures. Each source is too dim to see individually across the vast intergalactic distance, but together their collective hum creates a detectable, uniform radiance. Yet there is a compelling and more dramatic alternative. This glow might not come from stars at all, but from the truly diffuse, superheated plasma that fills the space between them. The galaxy could be threaded with a thin, searing gas at temperatures of 1,000,000 degrees or more, a cosmic atmosphere heated by the relentless shockwaves from supernova explosions. For millions of years, these expanding shells of debris have been slamming into the interstellar medium, transferring their immense kinetic energy into heat and creating a pervasive high-temperature fog. Disentangling these two possibilities is a monumental technical challenge. It requires X-ray telescopes with exquisite spectral resolution, capable of seeing subtle differences in the energy signature of the light. The spectrum from a collection of point sources would look different from the smooth thermal signature of a truly hot gas. So far, the evidence suggests a complex mix of both, a layered soundscape where the murmur of the crowd blends with the low roar of the galactic wind. This faint glow is a fundamental measurement of the galaxy's total energy budget. It reveals how efficiently the violent deaths of massive stars recycle their energy back into the galactic environment, potentially heating the gas so much that it suppresses future star formation. By listening to this faint X-ray whisper, we are not just studying individual objects, we are taking the temperature of the entire galaxy and hearing the echo of its most violent history written in a light we cannot see. Scattered among the ancient stellar populations of the Small Magellanic Cloud are brilliant blue rebels that refuse to fade with age. Known as blue stragglers, these stars burn with a fierce, youthful light that stands in stark defiance of their surroundings. They are found nestled within dense, ancient globular clusters where all the other stars are old, cool, and red, having long since settled into their final, sedate stages of life. In these celestial retirement homes, the blue stragglers are the vibrant outliers, shining with an energy that should have been extinguished billions of years ago. Their very existence presents a paradox, a cosmic case of a senior citizen running a marathon while their peers rest in rocking chairs. How can a star remain so young and hot when every other sun in its neighborhood has aged gracefully into dimness? The leading theories point to two distinct paths to stellar rejuvenation, both born from the crowded, social dynamics of these dense star clusters. The first is a story of cosmic violence, a stellar collision. In the packed core of a globular cluster, stars can swing so close to one another that their immense gravity pulls them into a catastrophic merger. Two older, slower-burning stars slam together, combining their mass and fuel to create a single, new, more massive and hotter star. This newly forged sun resets its evolutionary clock, blazing with a blue intensity that makes it appear far younger than its individual components. The second theory involves a quieter, more insidious form of theft. Many stars are born in binary pairs, and in a close orbit, one star can begin siphoning hydrogen fuel directly from its companion. This transfer of fresh fuel rejuvenates the receiving star, stoking its nuclear furnace and allowing it to burn brighter, hotter, and longer than a solitary star of the same age ever could. It is a stellar vampire, draining the life from its partner to sustain its own brilliant facade. The prevalence of these blue stragglers in the Small Magellanic Cloud is not just a curiosity, it is a direct measure of the galaxy's hidden activity. By counting them, astronomers can gauge the frequency of both stellar collisions and tight binary systems within these ancient clusters. A high number of blue stragglers suggests a dynamically lively past, a history of frequent gravitational encounters and cosmic car crashes. A lower number implies a more tranquil history where stars have aged in relative isolation. These rebellious blue stars are therefore celestial forensic tools, their brilliant light illuminating the invisible gravitational dance that has shaped the deepest, most crowded neighborhoods of our small galactic companion for billions of years. This river of gas is not empty, stretching across 75,000 light-years of near-nothingness. The Magellanic Bridge is a fragile filament of hydrogen connecting the small and large Magellanic Clouds, a celestial umbilical cord forged by their mutual gravitational pull. As the two dwarf galaxies swing around each other in their cosmic dance, their tidal forces have acted like colossal hands, reaching in and pulling out vast streams of primordial gas, stretching it into a filament so thin and diffuse it would be considered a near-perfect vacuum in any laboratory on Earth. Yet within this tenuous ribbon, against all odds, the first sparks of new stars have begun to flicker. This is star formation pushed to its absolute limit, a desperate act of creation in the most isolated environment imaginable. The gas here is not dense and cozy like it is within a galactic disk. It is sparse and stretched, a thin soup where gravity struggles to gain a foothold. For a star to be born here, vast clouds must collapse over immense distances, a slow and uncertain process compared to the vigorous star birth within the galaxies themselves. The stars that do ignite are often solitary, burning in profound isolation, with no stellar siblings for light years in any direction. These are the runaway stars of the intergalactic void, true orphans of the cosmos. They did not achieve their loneliness by being flung out of a crowded cluster. They were born into it, their cradle a river of gas adrift in the darkness between galaxies. Their light is a lonely beacon, telling a story of gravitational tides so powerful they can pull out the raw ingredients for suns, and of a universe where the urge to form new stars can ignite even in the deepest, most empty spaces. What must it be like to be such a star, to shine with no planets, no neighboring suns, with only the faint, distant smudges of your parent galaxies for company? These stellar hermits are natural laboratories, their pristine environment free from the pollution of countless supernovae. Studying them offers a glimpse into the most fundamental, unaltered process of star formation, a process that might have been common in the early universe before galaxies fully took shape. Their very existence blurs the line between galaxy and void, proving that the cosmos does not respect our tidy categories, and that life, in the stellar sense, can find a way even in the most unexpected and inhospitable of places. Its final nuclear fires have gone quiet. A star known only by the catalog number J00444 1.04-732136.4 is now in one of the briefest and most revealing phases of stellar life. This is a post-GB star, a celestial body in a state of profound transition. Having exhausted the helium fuel in its core, it has ceased all fusion and is now coasting on its residual heat, a dying ember whose outer layers are slowly but relentlessly drifting away into the void. It is caught in a perfect, fleeting moment, like a soap bubble that has just been blown but has not yet detached from the wand. Soon, the intense ultraviolet radiation from its exposed, superheated core will ignite this expanding shroud of gas, transforming it into a full-fledged planetary nebula. But for now, it offers an unobstructed view into the stellar alchemy that has been happening deep within. The light from this star is a cosmic confession, its spectrum a detailed inventory of its internal nuclear processes. When astronomers break this light down into its constituent colors, they find the unmistakable signatures of exotic heavy elements, specifically strontium and barium. These are not the common ashes of hydrogen or helium fusion. They are the products of a slow and delicate process known as the S process, where neutrons are slowly captured by iron nuclei deep within the star's heart over thousands of years. This gradual addition transforms the iron into heavier and heavier elements, building them up one neutron at a time like adding bricks to a tower. The fact that we can see these elements so clearly on the star's surface is the crucial part of the story. During its final turbulent years as an GB star, powerful convection currents acted like a colossal elevator, dredging these newly forged metals up from the hidden furnace of the core and depositing them directly into the star's atmosphere. Now, as the star sheds its outer layers, it is releasing these S-process elements directly into the interstellar medium of the Small Magellanic Cloud. This single, fading star is therefore a vital pollution source for its entire galaxy. The strontium and barium we see in its spectrum are the very seeds for future generations of stars, planets, and perhaps even life. In a galaxy that is naturally metal-poor, this chemical enrichment is a precious event. By studying J004441, we are witnessing a key delivery mechanism for the universe's heavy elements, watching as a dying star scatters its metallic ashes to the cosmic winds, ensuring that its death gives birth to a more chemically complex future. This cosmic debris might be more than just scattered wreckage. Within the sprawling tidal tails of the Small Magellanic Cloud, dense knots of gas and newborn stars are coalescing into something unprecedented. These are not mere clouds, they are tidal dwarf galaxy candidates, celestial infants being born from the violence of a galactic collision. Their origin story is completely different from that of their parent galaxy. The Small Magellanic Cloud itself formed long ago within a vast cocoon of dark matter, the invisible gravitational scaffolding that guides the birth of all primordial galaxies. But these new objects are emerging from pure chaos, assembled solely from the gas and stars ripped out during the gravitational tug of war with the Large Magellanic Cloud. They are built from the visible, tangible debris of the collision, not from a pre-existing dark matter halo. This distinction is a direct challenge to our fundamental understanding of what a galaxy is and how it comes to be. If these knots can hold themselves together through their own self-gravity, they will become true, independent galaxies, but of a new and strange type. They would be dark matter deficient, a characteristic that would make them unique in the cosmos. How can a galaxy hold itself together without the dominant presence of dark matter? The answer lies in the sheer density of the material from which they are forming. The tidal forces that pulled them out also compressed them, creating such a rich, dense environment that the mutual gravitational attraction of the gas and stars alone might be enough to bind them into a lasting structure. We are essentially watching a galactic birth in real time, a process that normally happened billions of years ago. These infant systems are natural experiments, testing whether a collection of stars and gas can survive as a coherent unit without the hidden hand of dark matter to guide it. Their success or failure will rewrite the rules of galaxy formation, proving that new galactic life can spring directly from the ruins of old. The heart of the Small Magellanic Cloud is a place of profound silence. Where our own Milky Way boasts a brilliant, crowded bulge of ancient stars and a supermassive black hole millions of times heavier than our Sun, the SMC's core is strangely serene. It has no dense stellar nucleus, no great gravitational anchor pulling everything into a tight, swirling dance. This absence is a galactic anomaly, a missing engine that should by all rights be there. So where is the monster that should be lurking in this galaxy's heart? One possibility is that it simply never formed. Building a supermassive black hole requires a specific recipe of dense gas, rapid star formation, and a chain of successive mergers between smaller black holes and star clusters. The Small Magellanic Cloud, with its turbulent history and lower density, might have never gathered enough material in one place to start that process. It is a galaxy that skipped a crucial step in its development, forever remaining in a more primitive, unanchored state, but there is a more violent explanation. The SMC has been gravitationally harassed by its larger neighbors for billions of years. During a close encounter with the Large Magellanic Cloud, the immense tidal forces could have reached right into the galaxy's core and ripped the nascent supermassive black hole clean out. The gravitational slingshot would have sent it flying into intergalactic space, a dark fugitive leaving behind a galaxy with no central soul. This quiet center has shaped the entire life of the dwarf galaxy. Without a central gravitational pivot, the motions of its stars are more chaotic, less organized into a clean, rotating disk. Star formation is not as centrally concentrated, instead scattered in pockets across its length. The galaxy itself is more fragile, more easily stretched and distorted by external forces, as the vast Magellanic Stream so clearly demonstrates. This profound silence at its core is not a sign of peace, but a ghostly fingerprint of a violent past, a theft that left an entire galaxy forever unmoored. Its steady rhythm is a stellar heartbeat set to a frantic tempo. SMC 10892 is a delta Scuti variable star, a pulsating A-type star whose entire surface rhythmically expands and contracts with the precision of a cosmic metronome. These stars are the younger, hotter, and faster cousins of the Cephid variables, completing their entire cycle of brightening and dimming not over weeks but in a matter of hours. This rapid, predictable pulse makes them invaluable tools for astronomers, another class of standard candle to illuminate the vast darkness between galaxies. The physics behind this pulse is a delicate dance between two opposing forces. The star's own immense gravity constantly pulls inward, trying to collapse it. At the same time, the intense heat and radiation pressure from nuclear fusion in its core push outward, trying to blow it apart. In a delta Scuti star, these two forces do not reach a perfect standstill. Instead, they fall into a resonant vibration, causing the entire star to breathe in a continuous, rhythmic pulse. As it contracts, it grows hotter and brighter. As it expands, it cools and dims slightly. This creates a reliable, repeating pattern of light that astronomers can track with exquisite precision. The true value of this pulse lies in the period-luminosity relationship. Just like with Cepheids, the very rhythm of the star's heartbeat is directly tied to its true, intrinsic brightness. A star with a longer pulse period is inherently more luminous than one with a shorter period. By simply timing the interval between its pulses from Earth and measuring how dim it appears in our sky, we can calculate its distance with remarkable accuracy. It is a fundamental celestial yardstick, yet when we point this yardstick at SMC 10892 in the Small Magellanic Cloud, we find its measurements are not quite standard. The low metallicity environment of this dwarf galaxy, its lack of heavy elements, changes the internal physics of the star. Metal-poor stars are more transparent, allowing heat to escape more efficiently from their interiors. This changes the way the star pulsates, subtly altering the precise relationship between its pulse and its power. The rhythm might be the same, but the volume of each beat is different from that of a similar star born in the metal-rich environment of our own galaxy. This is not a flaw in the tool, but a vital clue. By studying the specific pulsations of SMC 10892, astronomers are not just measuring a distance. They are calibrating the tool itself. They are learning how to adjust the period-luminosity relationship for stars born in different galactic environments, for stars that are built from more primitive, pristine material. Each precise measurement of its flickering light fine-tunes our models of stellar interiors. It tells us how the lack of metals affects the opacity of a star's layers, how it changes the way energy moves from the core to the surface, and how that ultimately governs the star's resonant frequency. This one star's frantic heartbeat is a tuning fork for the cosmos, ensuring that when we use its cousins to measure the most distant galaxies, we are hearing their true distance, not an echo distorted by the unique chemistry of their birth. Amidst the galaxy's vibrant glow, a patch of profound coldness stubbornly resists the light. This infrared dark cloud is a cosmic void, a silhouette of absolute blackness that stands out not because it shines, but because it swallows the very infrared radiation that passes through it. These are the coldest places in the entire Small Magellanic Cloud, regions where temperatures plummet to just a few degrees above absolute zero. Within these frigid, dense knots of gas and dust, gravity works its slow magic, pulling material inward in the first, silent steps toward creating new suns. These are not just any stellar nurseries, they are the exclusive birthplaces for the most massive stars in the universe, the colossal blue giants that will one day dominate their galactic neighborhoods. The darkness here is not empty, it is pregnant with potential. Finding such a cloud in the SMC is like discovering a perfectly preserved fossil. The galaxy's unique environment, with its lower dust content and simpler gas chemistry, makes this cloud a pristine laboratory. In our own metal-rich Milky Way, star-forming clouds are polluted with complex grains of carbon and silicate, which act as incredibly efficient coolants. This allows the gas to fragment easily, leading to the birth of many small to medium-sized stars. But here, in the more primitive conditions of the Small Magellanic Cloud, the dust is different. It is composed of smaller, sharper, and more transparent particles. This primitive dust is far less effective at radiating heat away. How does this fundamental change in the building blocks affect the star formation recipe? Without efficient cooling, the collapsing cloud cannot easily shed its internal heat and pressure. This might prevent it from breaking apart into smaller clumps, instead encouraging the entire structure to collapse into a single, monstrously massive star. It is the cosmic difference between a firework that sprays out 100 small sparks and a single, concentrated stick of dynamite that delivers all its energy in one colossal blast. By studying this one dark silhouette, astronomers are witnessing the initial conditions of star formation as they were in the early universe, a time before countless supernovae had enriched the cosmos with heavy elements. This cold, dark cloud is a window back in time, showing us how the first and most brilliant stars were conceived in the cold, clean darkness of a younger, simpler cosmos. That faint, rhythmic pulse from a variable star is a gentle whisper compared to the violent, focused scream of a cataclysmic variable. In this particular binary system, the white dwarf is no ordinary stellar cinder. It is a cosmic magnet of unimaginable power. Its magnetic field is so immensely strong that it completely dominates the space around it, reaching out and seizing control of the very gas flowing from its unfortunate companion star. This is not a gentle siphon, it is a brutal, directed funnel. The stream of stolen hydrogen does not form a chaotic, whirling disk as it does around other stellar predators. Instead, the white dwarf's magnetic field acts like a set of invisible, rigid rails, channeling the incoming gas directly down onto its north and south magnetic poles. This creates two incredibly intense, searingly hot spots at the points of impact, each one a constant thermonuclear explosion as the gas is compressed and heated to millions of degrees upon arrival. The energy released is so focused and ferocious that the entire system emits strongly polarized light, a strange and telltale signature where the light waves vibrate in a single, preferred direction, as if filtered through a cosmic lens. These systems, known to astronomers as polars or intermediate polars, are more than just celestial curiosities. They are perfect natural laboratories. Within them, we can study the physics of accretion pushed to an extreme, watching how matter behaves when it is not free to spiral inward, but is instead forced to follow the strict dictates of a magnetic cage. The chaotic, turbulent flow of gas is tamed and directed, allowing us to see the raw process of mass transfer with a clarity impossible anywhere else. What does it mean for a star to have a magnetic personality this dominant? It fundamentally changes the relationship between the two stars, creating a dynamic of control and submission that is written in the very light they emit. The silent dance of these 50 strange objects might one day send tremors across the cosmos. Far from the brilliant nebulae and runaway stars, some of the most massive binary systems in the Small Magellanic Cloud are locked in a slow, fatal spiral. Their destiny is not a flash of light, but a shudder in the fabric of spacetime itself, a gravitational wave. These future events will be so powerful that they could be detected by observatories like LIGO and Virgo billions of years from now. The key to this future violence lies in the galaxy's unique chemistry. The Small Magellanic Cloud is a low metallicity environment, meaning its stars are built from gas that is poor in heavy elements. This simple fact changes everything about how they die. In our own metal-rich Milky Way, massive stars tend to have powerful, dense stellar winds. They blow away their own outer layers over their lifetimes, shedding mass like a tree shedding leaves in a storm. This gradual weight loss can cause a binary star system to widen its orbit, preventing the two stars from ever getting close enough to merge. But in the pristine environment of the SMC, the story is different. Here, stellar winds are weaker and thinner. The stars hold onto their mass with a tighter grip. When a massive binary system forms in this galaxy, the two stars are more likely to remain massive and close throughout their lives. They do not waste away. When the first star explodes as a supernova, the kick it receives is less likely to tear the binary apart because the system is more tightly bound by the sheer mass of its components. The result is a system that survives the first stellar death, leaving behind a neutron star or black hole that continues to orbit its massive partner. Then, when the second star reaches its end and collapses, you are left with a tight pair of dark remnants, two black holes or two neutron stars circling each other in a final, intimate dance. Over millions or billions of years, their orbit decays as they radiate energy away in the form of gravitational waves. They spiral inward faster and faster until they finally collide and merge in a cataclysm that shakes the universe. This merger releases more power in a fraction of a second than all the stars in the observable universe combined, a burst of pure gravitational energy. The SMC is a perfect factory for these events. Its quiet, simple chemistry creates the ideal conditions for forging the tight, massive binaries that become these cosmic tremors. Every brilliant, unstable binary we see today, like HD 5980, is a potential candidate. Every runaway pulsar could be a remnant flung from such a system. We are looking at a galactic nursery for the most violent collisions in existence. While our telescopes see the light of these strange objects today, our gravity wave detectors are listening for the echo of their final acts, a deep thrum from a small galaxy that teaches us how the universe rings like a bell. The final strange object in this galaxy is not a star or a nebula, but the very fabric of the Small Magellanic Cloud itself. Every measurement of its starlight reveals a profound chemical simplicity, a deficit of heavy elements that seems at odds with its long and turbulent life. This galaxy should be richer, more chemically complex. It has forged countless generations of stars, and those stars have lived and died, scattering their metallic ashes back into the interstellar medium. Yet the galactic ecosystem remains stubbornly primitive, its stars built from a purer, more primordial stock of hydrogen and helium than we would ever expect. This is the overarching metallicity mystery, and it paints the entire galaxy as a single, coherent anomaly. How can a galaxy have a history of star formation without the corresponding chemical enrichment? The leading theory points to a galaxy that is fundamentally leaky. The supernova explosions that should be polluting the galaxy with heavy elements may also be acting as a cosmic cleaning service. In the low-gravity environment of a dwarf galaxy, the tremendous energy from these blasts can easily overcome the galaxy's weak gravitational pull. Instead of falling back to seed new stars, the metal-enriched gas is blown clear out into intergalactic space, lost forever. It is a galactic exhaust system, venting the very products of stellar evolution into the void and leaving behind a chemically stunted galaxy. The alternative is a story of dilution. The Small Magellanic Cloud may be a perpetual cosmic teenager, constantly accreting fresh, pristine hydrogen gas from the vast reservoirs of the intergalactic medium. This inflowing gas, completely free of heavy elements, would constantly dilute the galaxy's chemical soup, keeping its overall metallicity low despite the ongoing nuclear furnaces within. It is like trying to sweeten a lake by adding a cup of sugar, while a river of fresh water is constantly flowing in. The galaxy's chemical evolution is stuck in a cycle of 2 steps forward, 1 step back, forever maintaining its youthful, primitive state. This fundamental characteristic makes every one of the 49 other strange objects we have explored even more significant. The runaway pulsar, the missing neutron star, the warped accretion disks, each one operates under a unique set of physical rules dictated by this simple chemical environment. The strangeness we see is not a collection of isolated curiosities, but the direct consequence of a galaxy that has chosen, or been forced, to remain a chemical infant in a mature universe. The Small Magellanic Cloud is a 50-part puzzle where the final piece is the background upon which the entire picture is painted. a canvas of pristine gas that makes every brushstroke of stellar violence stand out in stark, brilliant relief. From runaway pulsars to stellar vampires and galactic tidal tails, this small galaxy has proven to be a universe of anomalies in miniature. Each of the 50 strange objects we have encountered is a fundamental question, a cosmic riddle that challenges our understanding of physics. The Small Magellanic Cloud, our closest galactic neighbor, is not a simple collection of stars. It is a dynamic and violent frontier, a place where stars defy their own lifespans, where black holes feed in silence, and where the very fabric of dark matter is put to the test. It forces us to admit that for all our sophisticated models, the universe still holds profound mysteries right next door. This faint smudge of light in the southern sky is a constant reminder that discovery is not always about looking deeper into the void, but about looking more carefully at what has been beside us all along. So the next time you find yourself under a clear, dark sky, look toward the southern horizon. If you are lucky enough to see the Magellanic Clouds, know that you are not just seeing faint clouds. You are looking at a celestial laboratory, a place where the rules are being rewritten with every new observation. Let that sight be a reminder of the endless mysteries waiting in the darkness, urging us to keep looking up, to keep questioning, and to never lose our sense of wonder at the cosmos we call